Okay. Welcome everybody to lecture 26 of CSE 548, the analysis of algorithms. Let's start off. First of all, are there any questions about any of the material or anything like that? Question?
Are the graduate presentations open, or is it just?
The graduate presentations. Question about the graduate presentations. I'll set the times for the graduate presentations next class. Basically, what we'll do is I'll arrange a one or hopefully two different times during finals week when the graduate students can come and make a quick presentation. I'll announce the times next class. I want to synchronize that with some other people because I want to videotape the presentations so people can see how they look. Don't worry about the presentation if you're a graduate student. Okay, I mean it will not count towards your grade. Okay, but it's a good experience, I think, to give a presentation and see what you look like on video. This semester, for example, I've had an extensive chance to see what I look like on video. Okay, and it's a useful thing, and and I think it's good for people to give presentations. Okay, if you know what you're talking about, it's good practice to try to figure out how to boil that down and say in 5 minutes, give some kind of a quick overview of what you do. Pick out something important and talk about it. And if you don't know what you talk about, it's probably good to learn how to give presentations anyway. Okay, just to sort of learn how to fake it. Okay, any questions about the presentations? I'm sorry I don't have the times, but we'll talk about that next class. And if for some reason somebody has a religious objection or something like that to being videotaped, don't worry about that. We'll work around that. Okay, or for some reason somebody absolutely can't make one of the two times, we can work around that. Any questions about the videos? Or yes?
What's the due for final project?
Your final projects are due the last day of class. So I'll let you guys have till Friday, till I leave here on Friday. Okay, which will be about 3 o'clock. Okay, on Friday. So at the CS department donut hour on Friday, I expect to have all the projects by then. Yes.
So we should submit reports.
Right. So if you're doing a project, basically I'll expect some kind of a report, some kind of a document that you'll have turned in to show what you've done. If you'd written a survey paper, obviously that would be you've got to turn in the paper. That's your project. If you've done an implementation, you should give me at least a brief write-up about what this implementation is. Show me a copy of the code, a print report with the copy of the code and the results of running it, what you did, and something like that. So I basically want to be able to figure out what you did. If you were working on an open problem, I want to see sort of what did you learn about the problem. I don't expect people to solve it. I don't expect that, but I do expect people to show some kinds of evidence that they understand the problem in some reasonably deep way, that they got caught at a point. I know where they got caught, okay, or know that, let's say, some special case that they figured out. Okay, or something like that. And basically a report describing what you've done, okay, should hopefully make clear what you've been thinking about.
Do we need handing the source code? Because I do implementation.
Okay, if you do an implementation, yes, you have to hand in the source code. Turn in a printout of the source code, and if it's more reasonable to email me the source code, that's fine. Although I'd like to see a printout, maybe very fine, just so I can get some rough idea, so I can glance at it. Just give the printout for the source code and the results of running it, and some report describing why you were doing this. Okay, so don't just give me an undocumented program and say this is my project. That would be a bad thing. Okay, any questions about the projects? Okay, and any questions? Next class I'll talk about the final exam and things like that. Okay, question?
And which Friday is the deadline? This one or next week?
This Friday. This Friday. So it's the end of classes this Friday, donut hour, 3 o'clock. Okay, is when they're all due. Okay? Any questions?
How much will the final encompass?
The final will encompass everything that I cover during the semester. Okay? With the possible exception of what I cover in the last class. Okay? I haven't decided. Depending on how far I get today, I may cover some more optional material towards the end. But I'll let you know what's on the final. You can assume everything we've covered so far is on the final. But we'll talk more about the final next class. Any other questions? Okay. First of all, the problem of the day asked how to prove that the Hamiltonian path problem is NP-complete. And the important thing to see here is first, that in doing the reductions, this semester I just chose not to cover the reduction the proof that Hamiltonian cycle problem is NP-complete. So I didn't actually go through that reduction. But on the other hand, it's in the book. You should be able to assume it. It would make sense that to prove the Hamiltonian path problem is NP-complete, you'd want to start from the Hamiltonian cycle problem. But it isn't quite trivial that, to prove that Hamiltonian path is NP-complete given Hamiltonian cycle. You can't say just it's the problem of Hamiltonian cycle is NP-complete. Okay. Well, actually, wait. I guess there's a couple different ways you can do it. And I think I may have had another proof up here. It's not a simple thing to say that Hamiltonian path is a special case of Hamiltonian cycle. You've got to be a little bit careful about that, because certain graphs, what you're really looking for is, again, a program to solve Hamiltonian cycle calling Hamiltonian path. That's how you would prove that Hamiltonian path is hard. Okay? Now, it is not true. While it's true that any Hamiltonian cycle problem has a Hamiltonian path, okay, because if you take a cycle and you delete an edge, you're left with a path. It's not true that every graph with a Hamiltonian path has a Hamiltonian cycle. So you've got to be a little bit careful in how you do the reduction. Okay? So, okay, a question.
But don't we have to map all instances for Hamiltonian cycle to at least one instance of Hamiltonian path?
You have to map all instances of Hamiltonian cycle to an instance of Hamiltonian path. But you may have to, you can't just say sort of, does this graph have a Hamiltonian path? Because that graph may, you can't just say, does G have a Hamiltonian path? Because G may have a Hamiltonian path but not have a Hamiltonian cycle.
You may add some restrictions to the path to make it a cycle.
So the question is now, how do you make it a, so one idea could be, actually, and I think that one possible case that I think that he's alluding to, you could say, is there a Hamiltonian path from vertex S to vertex S, where S is some vertex in the graph? And I guess that's actually, if you're allowed that kind of a query, which seems like a reasonable one, okay, that would probably be a legitimate way to solve it quickly. Okay, if you've got a subroutine like that. Okay, question.
If given a Hamiltonian path graph, and given the proviso that if I added one single edge, that would then form a cycle, and from that assumption, could I then prove it?
Okay, so the question is now, how would you go about doing it by adding edges or so? And the way that I would say the easiest argument, okay, that finding a Hamiltonian path in a graph is hard, is that if you could compute Hamiltonian path efficiently, okay, you could test whether the graph has a Hamiltonian cycle. So that right now what was proposed here is if we assume the degenerate case we're allowed to ask the same starting and ending vertices, okay, then the Hamiltonian path is the same. That's probably an okay way to prove it, I guess, assuming you're allowing your Hamiltonian path is strong enough to do that. If you want to be a little bit weaker about it, okay, you could say that you could solve Hamiltonian path, okay, you could solve Hamiltonian cycle using Hamiltonian path by repeatedly taking an edge from that graph, deleting it, and asking if there's a Hamiltonian path between those two vertices whose edges you deleted it. So by making m calls, m being the number of edges, to Hamiltonian path, clearly you could solve Hamiltonian cycle. And since m is polynomial in this thing, that should be a proof that that should be a convincing proof that that Hamiltonian path is hard to solve. Because by calling this thing m times, you could certainly solve Hamiltonian cycle by just repeatedly deleting a different edge. In fact, all the proofs that we've done have only called our magic oracle here, our unknown problem, once. And by modifying the construction that was used in the book from vertex cover to Hamiltonian cycle, replacing it so instead of having a cycle, one has a deliberate start and end point and uses less vertices. I didn't go through this reduction, but by modifying this reduction, one can in fact find a direct proof that only calls it once. Okay, by reducing vertex cover to a graph which has a Hamiltonian path, if and only if that thing has a cover of size k. Okay, I didn't go through that proof, but that reduction. But you can look at it in the book or in my notes if you're interested. Okay, any question? Okay, fair enough. Okay, so far I've spoken a lot about, we've proven a lot of different problems NP-complete. Okay, we proved vertex cover, we proved clique, we proved set partition, subset sum, we proved 3 satisfiability. There's lots and lots of NP-complete problems out there. Okay, I'm not going to try to prove them all. Okay, what are examples of hard problems? One problem that we basically sort of talked about, can you partition a set of n integers into 2 equal subsets such that the sums of both sets are equal, okay, or almost equal? That's a hard problem. The problem of bin packing. Suppose, let's say that I give you a set of bins of a particular size, and I give you, a set of items of particular size. Can you pack all the items into the bins? Okay, that problem is NP-complete. Given a graph, okay, we say that we color a graph whenever 2 vertices of the graph, okay, whenever there's an edge between 2 vertices, both vertices have to have different colors. Okay, so for example, if we have a graph like this, we've talked a little bit about bipartite graphs. Now let's make this a graph like this. Here we've got a graph on 5 vertices. If I want to make sure that no 2 neighboring vertices get the same color, what can I do? I can color this vertex blue. I could color this vertex white. Okay? I could color, let's just think about how I do this. I could color this vertex red, this vertex blue, this vertex white, and with 3 colors I can color this graph, such that no edge touches that thing. Finding the minimum number of colors you need, okay, which comes up a lot in scheduling problems, okay, that problem is NP-complete. Given an n by n checkerboard, I don't know how many people are familiar with the game of checkers, okay, I guess some people, sometimes it's called drafts or draughts or something like that if you're from England. But checkers is a famous children's game. You've got, a checkerboard, okay, something that looks like this. And you've got pieces on the checkerboard, and your goal is to somehow capture all the other guys' pieces. Suppose I give you a checkerboard with n by n, an n by n checkerboard, so n is part of the input, and a particular with a particular set of pieces on it. Some white, some red. And I ask you, does white have a win from this position? Okay, is white guaranteed a win? That problem is NP hard. Okay, a lot of problems in optimizing programs, okay, in scheduling, in lots of different things are all NP-complete problems. So you shouldn't be surprised. A lot of the problems we've looked at were hard. Many problems that people are interested in are hard problems. Okay, and that's why you have to be aware of them. There's a few problems that are famous because we don't know whether they're hard or if there are polynomial algorithms for it. And the interesting thing is how few problems fall into this category. There's a lot of problems for which we know efficient algorithms. There's a lot of problems for which we know that the problem is hard, and therefore there won't be an efficient algorithm unless something strange happens. What's amazing to show how powerful these two tools are is how few problems people have looked at that they don't know whether the problem is hard or easy. Okay? These are basically the only 3 famous problems that people don't know whether it's hard or not. I mean, there's some other problems people are curious about, but these are the ones that are most interesting. The problem of graph isomorphism. If I give you 2 graphs, okay? Here I've got 2 graphs. Here's a star on 5 vertices. Here's a cycle on 5 vertices. Are these 2 graphs the same? Okay? In the sense that you could relabel the vertices of this to get that. That's the isomorphism problem. Okay? So given 2 graphs, is there a way to relabel the vertices of this such that it matches that? And in this case it is. If we make this vertex 1 is adjacent to vertices 3 and 4, according to this. Vertex 3 is adjacent to vertices 1 and 5. 5 is adjacent to 2 and 3. 4 is adjacent to 1 and 2. So yes, so these vertices or graphs are in fact isomorphic. Question?
Didn't we prove before subgraph isomorphism?
Subgraph isomorphism. But not graph isomorphism.
But wouldn't this be one of the cases?
Well,
The subgraph.
let's think about that. We proved that subgraph isomorphism was that. What did that ask? That asked, given some graph G and some graph H, is there a subgraph? Is H a subgraph of G? Okay? So in that case, how did we prove it was hard? We proved it was hard by given a graph G and a clique on K vertices, right? Those were the specific graphs. We said, is this a subgraph of that? Okay? If we had a graph, a procedure for doing subgraph isomorphism, we could give it G and H, two graphs of the same number of vertices, and ask, is this a subgraph of that? So using subgraph isomorphism, we could solve graph isomorphism. Correct? Because subgraph isomorphism says you're given one graph and another graph is the other one in this. Okay? If we gave them two copies of two graphs with the same number of vertices, that would be the graph isomorphism problem. So you could use subgraph isomorphism to solve graph isomorphism. But you can't do it the other way around. Question?
Would the same reduction with clique work in this case? So if you give a graph on n vertices and give a clique
On n vertices.
on n vertices,
Well, how hard is it to tell if I give you a clique on n vertices? And how hard is it to tell if I give you a graph, is it a complete graph on n vertices? It's trivial. Okay, you look at every vertex. Is every vertex adjacent to n minus 1 other vertices? Yes. Okay? So testing if a graph is a clique, okay, is an easy thing. Testing if a graph has a clique as a component to it is what's hard. So testing if one graph contains another is provably hard. Testing if two graphs really are the same thing, okay, is what's not known how to do. Okay? And it turns out to be a very interesting distinction. How many people see the difference, what I mean by the distinction between graph isomorphism and subgraph isomorphism? Okay? And is there anybody who's confused about why subgraph isomorphism is hard and graph isomorphism might not be? Okay? That's good. Another problem that's sort of famous problem is as a famous hard problem or a known problem is given a graph, given a number, okay, can it be factored into two numbers that multiply to it? Okay, so if I give you some number 2,763,842, can you factor that into two integers that multiply to that? That problem, no one knows whether that problem is polynomial or not. Okay, I mean there's various reasons for believing certain things, but it's an example of one that people don't know about. And one problem we looked at in class a little bit. Given a set of points, finding a triangulation of minimum length. Remember what a triangulation was? It was something like that. Finding a triangulation where the length of the edges you add is minimized. No one knows in general whether that problem is NP-complete or not. In class, we gave an algorithm for the very special case where the points had to lie on the convex hull. We're on convex position. If we allowed interior points, our dynamic programming algorithm wouldn't work. But no one knows whether that problem is hard or not. Okay? Any questions about that? Okay? Yeah, question.
Back to subgraph.
Right.
Back to graph isomorphism.
Right.
For example, if we have as our subgraph problem, we have graph G as a star.
Right.
And we check if H cycle of 5 vertices is a subgraph of it.
Okay, let's try to prove it. You want to try to prove graph isomorphism is hard. Right. How do we prove graph isomorphism is hard? We take our known hard problem, which is subgraph isomorphism. Correct? And we feed as input to this thing a G and an H.
Right. And they have equal number of vertices.
Well, I didn't prove. You're now saying subgraph isomorphism, where two graphs have equal number of vertices, is hard. I didn't prove that. I proved that subgraph isomorphism, where one graph is much bigger than the other graph, is hard. Okay? You're now making a specific subproblem of that. which I have no reason to believe is hard. I didn't prove that the specific problem that you're claiming is hard. Subgraph isomorphism, if one graph was the, if the two graphs were the same size, is exactly the same as graph isomorphism. But that's an extra condition on the problem, and we didn't use it. We didn't prove anything with it. Okay? So you can't make a statement like that. Okay? Any questions about that? It's kind of an interesting point to see that slight changes in problems can make a big difference. And we've seen that throughout the semester. Okay? For example, we gave a problem, we gave algorithms like Dijkstra's algorithm to show that finding the shortest path in a graph between two nodes is polynomial, right? Using Hamiltonian path, you can prove that finding the longest path between two vertices is hard.
Wait, did you say Hamiltonian path or?
Hamiltonian path. If you think about it, Hamiltonian path is a question. If you start here and end here, can you visit all the vertices exactly once? That would be the longest path, simple path in the graph if it was possible. So finding the longest path is hard, shortest path is easy. Okay? Given a graph, an Eulerian cycle, okay, remember, is one that visits every edge exactly once. Okay? It's like corresponds to, can you draw the thing without lifting your pen off the paper? Okay? Eulerian cycle isn't polynomial, isn't B. It's very easy to do. It says, can you visit every vertex exactly once? Not every edge, but every vertex. That problem is hard. This problem is easy. Okay? Vertex cover, we discussed, was hard. That said, is there a find the smallest set of vertices such that every edge is covered? Correct? Edge cover would be the complement. The smallest set of edges such that every vertex touches one of your edges. Okay? Reverse the role of edges and vertices. This problem is in polynomial time. This problem is hard. Okay? And like we saw just before, the difference between graph isomorphism and subgraph isomorphism. 3 letters, but one of them is hard and one of them is the great unknown. Okay? So you've got to be very, very careful in how you define your problem. Statements about it being hard. Okay? That's sort of a fundamental thing here. Okay? Any questions about that? Okay? Now, what should you do if you have a problem that you suspect is hard? Okay? One resource that everybody should be aware of is this book by Gary and Johnson, okay, called Computers and Intractability. Okay? It's a nice book, paperback. You can see by how beaten up my copy is, how okay? That the reason for this is that this book describes, in the back of the book, it contains a list of over 400 problems that are known to be NP-complete. Okay, like for example here, let's just take a look at this one here. Okay, serializability of database histories. Okay, annihilation, which is a game, I guess. Okay, I hope. Okay, okay, simple. Lots and lots of different problems in here. It'll tell you whether it's hard. Hamiltonian completion. Okay, given a graph, can you add edges? How few edges do you need to make it Hamiltonian? Okay. Biconnectivity augmentation. How few edges do you have to add to a graph to make it biconnected? Lots and lots of problems are in here. Okay? And if you think your problem's NP-complete, one of the first things to do is to look in the back of the book to see whether or not your problem is just an amazingly useful resource. It's probably the book that I reach for most in day-to-day practice. Okay? Any questions? What? Judging by the condition, right. Okay? Any questions about that? So that's a thing to keep in mind. And if you like collecting algorithms books, that belongs in your shelf. It's one of the most important ones. Okay. How do you go about proving problems hard? I mean, proving a problem hard is a little bit of an art. Okay? And I mean, you can see and be sort of impressed by these reductions like we saw for subset sum or vertex cover, where you map one problem into wildly different things. How do you go about finding these things? Okay, how do you go about proving your own problems are hard? And there's 3 basic techniques. There's 3 kind of styles of proofs that people come up with. Okay? and you should be aware of them, sort of what the style is. The first idea, and the simplest thing, is the idea of using a restriction proof. What do we mean by restriction? If we can show that a special case of the problem is NP-complete, then our problem is NP-complete. Okay? So for example, we talked a minute ago about the problem of finding the longest path in a graph. Okay? Given an integer k and a graph, is there a path of length k? That problem we know is hard because it is simply a special case of it is Hamiltonian path. Hamiltonian path asks, is there a path of length n number of vertices? If we could solve it for the special case of n, okay, that would mean that we've proven that p equals np. If we could have a program that could solve it for all values of k, okay, find that is there a path of length k where k is part of the input, we could use it to find Hamiltonian path. So long as the problem that you have, okay, are interested in has a special case which is hard, then your problem is hard. Okay, this is a little backwards from what you might be thinking. Okay, like we were saying, graph isomorphism. Sure, a special case of graph isomorphism is subgraph isomorphism. Okay, but that's the wrong way to think about it. Okay, if our problem contains a subproblem which is hard, our problem is hard. Okay, and those are the easiest kind of proofs to come up with. What? Okay, the case where if you can prove that the problem you're interested in has a special case which is hard, your problem is hard. Okay, and these are the easiest kind of proofs. These are the kinds that tend to appear on exams. Okay, because they can be banged out very easily. Okay, and so it's important to look and see which problems we've looked at really are of that flavor. Question?
So then we just say it's a special case? Or
well, what does a special case mean? Okay, well, how do we prove something is hard? Go to the picture again. Here's your hard problem.
Okay.
Here's your hard problem. Here is your unknown. Once you know that your unknown problem contains a hard problem as a special case, okay, all you have to do is then reformat that hard problem, which is a special case of your general problem, specify what is the parameters that restrict it to that special problem. Then you've got your subroutine. Okay? Any questions about that? Whenever you're confused, go back to this diagram. Think Bandersnatch, think Bobilly. Okay? So make sure you get the right direction. Any questions? The second class of problems, which are possibly to appear on exams, but less likely, okay, are what we call local replacement ideas. Here's where you take a problem and you modify it a little bit. You tweak the structure of the problem, translate it slightly. Okay? The classic example of a local replacement problem is when we converted SAT to 3-SAT. If you think about it, we took every thing from our SAT problem, converted each clause, translated it basically independently, okay, into clauses of SAT. Okay? So these involve some slight modification of the problem. Okay? Another example of what I consider local modification would be to show that graph isomorphism is not an easier problem even when I tell you the graph is bipartite, meaning two-colorable. Why? Because if you have two graphs and you're trying to tell is this isomorphic to the other, if I modify each graph by adding a vertex between each edge, now the graph is bipartite because every edge goes between a new vertex and an old vertex. And certainly it isn't going to make it any easier to test if this graph is bipartite, is isomorphic just because I split each edge. Okay? So the problems are really the same. Okay? And now I've got bipartite graphs. Okay? So sometimes by doing a little tweak to the problem, you can prove something else about it. Okay? Something that's more special about it. This is usually how you find sort of refine the hardness to show that your problem stays hard even under certain conditions, like the graph is bipartite or your clauses have only length 3. Any questions? Okay. The final class of proofs, which are the big, ugly, majestic proofs that we've seen, these are often called component designs, where you really have to sort of alter one problem and map it to something else. These are often hard to do, although once you get the hang of them, actually they're surprisingly easy. Okay? They're actually a lot, no, this people will be surprised at. Okay? Once you look at enough of these proofs, it's usually a lot easier to bang out our NP-completeness proof than you might think. Okay? And, you know, we'll talk about that now. How do you actually go about doing an NP-completeness proof? Okay? What is sort of the tricks of the trade? Well, when I have a problem to prove that is hard, this is my procedure for doing so. Okay? Fairly often I'm faced with a problem, don't know if it's easy, don't know if it's hard. I try to come up with an algorithm, I fail. What do I do? Okay? How do I go about proving that a problem is hard? Okay? And the thing is that it's actually a lot easier than it looks, for the same reason that it's a lot easier to write bad programs than people outside think. Okay? How many people here have ever tried to modify somebody else's code? Okay? A lot of people. How many people found that a happy experience? Nobody. Okay? So when you look at, think about what a NP-completeness proof is. It's a translation, it's basically a program to map instances of one problem into another problem. When you try to understand somebody else's NP-completeness proof, to a certain extent what you're really trying to do is understand somebody else's program, which is a hard thing to do. What is often easier than trying to understand somebody else's program? Throw it out and write your own. And the same is surprisingly often true about NP-completeness proofs. Okay? It's usually easier to recreate them than to understand them. Okay? Once you sort of have the hang of it, which takes practice. I'm not going to lie about that. But this is the truth. So when I'm given a problem and I have to prove it's hard, what do I do? Okay? These are the rules of the tricks of the trade that I use. The first thing is to realize, what are you doing in an NP-completeness proof? You're taking a known hard problem and translating all instances of that into your problem that you don't know. If you want to translate all instances of a hard problem, your first thing to do should be to find as simple a hard problem as possible. Okay? Or in the sense that it requires as restricted a problem as possible. Why? Because the more restricted it is, the less work you have to do in translation. Okay? Which is going to be easier, to write a program that translates Russian to English, or a program that translate Russian conversations about baseball into English? Okay? Probably Russian conversations into baseball, because baseball is more restrictive. You don't have to worry about biology or politics or anything else. Okay? So how do we make our source problem restricted? Okay? The traveling salesman problem is NP-complete. But is that a restricted problem? No, you've got weights on all the edges. Okay? Maybe we can make the problem simpler. How can we make it simpler? Well, traveling salesman problem is hard even when the edges obey the triangle inequality. What does that mean? That means that the distance from here to here is going to be less than or equal to the distance from here to here plus the distance from here to there. That's a special case. Not all traveling salesman problems have that. Okay? But the problem stays hard for that. Even better, Hamiltonian cycle is a special case of traveling salesman, right? Where all the edges either have weight 1 or infinity. Okay? That's simpler, so maybe that's better to work with. But even simpler than that is the following problem. Hamiltonian path on directed planar graphs. Planar meaning they can be drawn without edges crossing, where every vertex has a total degree, in and out degree of 3. This problem is hard. This is about the most restrictive variation on traveling Hamiltonian path cycle that I know of. How do I know of it? I look it up in Gary and Johnson. Okay? So what's the point? Pick the simplest problem you can as your restricted problem. Okay? And All these problems are NP-complete. They're equally good to start from, but the simpler the problem, the less work you have in translation. Okay? How many people believe that? Okay? Any questions about it? Okay, that's good. That should be a point. Second thing is, you're trying to prove that the problem you're interested in is hard. Okay? To make it as easy as possible, you should make your problem as hard as possible. If I'm trying to prove that my problem is hard, I should do everything I can to modify my problem to make it even harder. Okay? Since usually the problem you're interested in is not completely perfectly defined at first, define it in a way to make it as hard as possible. Okay? Maybe add some extra constraints to it. Okay? Or extra freedom. Okay? Like, for example, if you wanted to prove, think about it the other way. If you wanted to prove Hamiltonian path was hard, pick the more general problem, traveling salesman. It'll be easier to prove traveling salesman is hard than something restricted like, the more restricted it is, the harder it is to prove it's hard. So try to fluff up your problem by adding extra constraints to make the problem, that unknown problem, as hard as you can before trying to attempt the translation. Okay? Any questions about that? Okay, that should be believable. What other secret? The single most important thing to do is make sure you start from the right problem. Okay? I agree that once you have the problem, you want to make your problem as restricted as possible. But how do you go and pick which problem to start from? You could go through Gary and Johnson, look through all 400 problems, and pick the one that sounds best. My usual technique is I stick to only basically about 4 kinds of problems that I know a lot about. Okay? That basically you guys know a lot about. Okay? 3 satisfiability. You've seen that. You know about 3 satisfiability. In theory, any problem will be any NP-complete problem is as good as any other. Okay? Almost all of them start from 3 satisfiability. Okay? So don't be afraid if you can't find a good problem. Otherwise, go back to 3 sat. It's usually pretty reliable. Okay? Once you know what you're doing. If you've got a number problem, the number problem we've seen so far, integer partition, subset sum. If it's a number problem, I say use that. If it's a graph problem, I say think about what is special about the graph problem I'm trying to prove. Okay? If the reason I think it's going to be hard is because I have to select something, okay, then I'd probably start from a problem like vertex cover. Vertex cover, what are you trying to do? You're trying to select vertices such that all the edges are covered. Okay? In clique, you're trying to select a subset of vertices with a certain property. If you're doing selection, you want something like a vertex cover, because that's really what selection is. If, on the other hand, the problem you have involves ordering, I would go back to Hamiltonian path or Hamiltonian cycle, one of those. Okay? Because there, the hard part is not to select the vertices, because all the vertices have to be there. It's to order them. Okay? And so limiting your attention to these 4, you can usually figure out which flavor is right. Okay? Any questions? Okay? Okay? One last page of advice before we go a little further. When you're thinking about actually doing the reduction, what are you trying to do? You now have to figure out, I want to translate this problem into that problem. Okay? And if you think about what defines a problem, it's usually some kind of constraint or something like that. You're saying you'd like to pick this provided this happens. Correct? That's really what is happening in a problem. Vertex cover. Pick the smallest set of vertices such that you get all the edges. Okay? So if you want to propose a vertex cover, you want to punish yourself if you pick a set of vertices that doesn't contain all the edges, right? So what is the tactic? You should be trying to figure out what punishment do you want to deal out. Okay? What is the thing that makes a solution to the problem that you're translating a bad thing? Okay? And then try to do your reduction so that when in the translated problem you're going to do something that you don't want to do, it costs you a lot. That's really the philosophy of what you're trying to do. Okay? There's good things and bad things when you do a translation. Make the things corresponding to constraints correspond to highly undesirable things in the translation. Okay? That's really, in some sense, what you want to do. Okay? Question? Can we give an example on this thing? Okay? So let's think about one of the reductions. I mean, for example, what was the idea behind translating the clauses? We had each clause. We wanted to translate it into a bunch of clauses such that the key point was we wanted to penalize ourselves for not having a true in that clause. How did we do it? Well, we mapped it to a set of clauses, okay? And our goal was, how can we make sure that there is a true in every single one of these? That was really what the idea, the thought process is. How do I take my SAT clause and translate it into 3 SAT clauses such that you better have a true in all of these? Okay? And I did that by adding these extra things. Okay? That's maybe not as good an example as happens in practice. But when I'm thinking about these, the reductions we've seen haven't really had this flavor as much as some of the others. Okay? But in your mind, you think, I want to make sure you do. And the way that I do that is by modifying my construction to punish you, okay, if you try to do that. Okay? Any question? Okay? If you think about one of these things, okay, your problem is, the way that I would think about it is you want to think in 2 levels. Whenever you think about any problem, there's a strategic level and a tactical level. Okay? Strategy is your great big vision of what. Okay? Tactics are once you've made a decision about what you want to do, how you go about doing it. Okay? And it's important to think about this at 2 different levels. Okay? So, for example, when you're trying to do a reduction, you should be asking yourself questions, how can I force that either this or that happens? One of these is taken, but not both of them. How can I force that this is taken before that? Okay? And how can I make sure that nothing is select? And then once you've got it, sit down and figure it out. Okay? Any questions? Final thing is, if you keep looking for an NP-completeness proof and you can't find it, okay, don't be afraid to start looking for an algorithm. One reason why it's often difficult to prove a problem is hard is because it may not be hard. Okay? And fairly often I've started trying to prove a problem is hard, gotten stuck and said, well, why don't I look for an algorithm? Okay? And then suddenly an algorithm becomes clear because I know why. Okay? So don't be afraid to bounce back and forth if you get stuck. Okay? Any questions about the strategy of proving problems hard? Okay? But how do I apply this, you're asking? Okay? You've given me lots of rules. How do I apply it? Okay? Well, we're going to now try something unprecedented on live television. Okay? I am going to now have a student pick a random problem from the back of Gary and Johnson. Okay? There's 400 problems in the back. I have certainly not seen NP-completeness proofs for any more than probably 10 or 20 of them. Okay? And those that I saw, I've probably forgotten most of them. Okay? What I'm now going to do is have a student pick a random problem from the back of the book. Okay? And let's now go through and see if we can come up with a proof on the fly. Okay? Okay? So let's see. Does anybody want to... Let's see how we're going to do this. Okay? Gary and Johnson has a set of a bunch of different problems in here. In this section, they have problems on graph theory, network design, sets and partitions, storage retrieval, sequencing, logic, automata theory, and programming languages, among others. Okay? Which one? Let's see. How many people? Let's try some votes here. How many people want a graph problem? Okay, a lot of people. How many people want a network design problem? No one. Okay. How many people want a set partition problem? Okay, a couple people. Okay, storage and retrieval. A few. Okay, sequencing? Nobody. Okay, logic? A couple people. Oh, logic some more. Okay, automata theory? A lot of people want it, but I don't think we want to do that because not everybody here knows automata theory. That's the reason. Program optimization. Okay, not so many. Okay, looks like it's a choice between a graph problem and a logic problem. How many people want a graph problem? Okay, how many people want a logic problem? Okay, I think the graph problems win. Okay, let's now go to a number here. Okay, there's a graph problem. In graph theory, he lists how many problems? Let's see, 60. He lists, what is it? 65 problems. Okay, I want to volunteer. Okay, pick a number from 1 to 65.
Okay, I choose 51.
51, okay, from the back. Uh-oh. Okay, so what is the problem here? Let's look at what is problem 51. Okay, let's look at it, zoom it up, let's try to understand the problem. Okay, I don't know how well this can be read. It's maybe not as flat as the other one. So what is the problem? Graph contractibility. How many people, can you read that from there? No. Okay, let's see if we can figure out a way to get this thing done. What? Zoom it in a bit more. The trouble is then we don't cover it completely. Okay, fine. Let's try this then. So what is graph contractibility? Given a graphs G and H, can a graph isomorphic to H be obtained from G by a sequence of edge contractions? Okay, i.e., okay, a sequence, okay, in which every edge step replaces two adjacent vertices, okay, by a single vertex adjacent to exactly those vertices that were previously adjacent to one of those. Okay? What is that problem? Okay, I've never seen this problem before, okay, so I'm getting a little nervous here. Okay? But what is the idea of that problem? Okay, we'll look at, you have to first understand the problem. What's the first step? Okay, it seems that you have a graph G and you have a graph H. Oh, sorry. Okay, let's try zooming it in a little bit now. It's a little hard to see where I am on the blank sheet. You've got some graph G, okay, big graph G presumably, and I guess a little graph H, right? And what was the question here? The question is, okay, is there a sequence of edge contractions, okay, where every, okay, can a graph isomorphic to H, sequence of edge contractions, okay, namely a sequence of operations on G, such that for every, that we take a pair of edges and contract them, meaning we take those two vertices, delete them, and replace them by edges from the new vertex to everything that the old ones were adjacent to. So this two were adjacent to each other. That's the edge that we're contracting. This vertex was adjacent to one other vertex. This vertex was that. So edge contraction would delete these two vertices and replace them with that vertex. Okay? Does everybody agree with that, or what an edge operation, contraction operation is? Okay? So let's try some examples. Okay? Can we get from here, this is what I do at first. I'm just sitting here trying to understand this problem. I've never seen it before. Okay? How would I understand it? Well, I start constructing examples. Can this be shrink these two vertices together, okay, and replace them by something else, right? I can basically take each edge and contract it, and that's going to be squashing my loop tighter and tighter, okay? Let's see, are there any other interesting examples? Can I create, let's say, suppose I have a tree. Is there any way I can create this from a tree? I think the answer is no, right, because I can't create any cycles, okay, if I didn't have a cycle before. Is that true? Let's just think, why is that exactly true? The only way I could create a cycle would be as if there was some edge from this subtree and that subtree, but then there'd be a cycle in the original tree. So that's a proof, okay? If I have a tree, I can't create that, okay? Let's see, anything else we want to figure out about contraction? I think we got some kind of an idea now. I'm starting to warm up this problem a little bit, okay? Starting to focus here. Because now I've got some idea about what contractions can do. Okay? Any questions about contractions or anything like that? Okay? Now what do? Maybe stalling for time, I read the problem again. Just to make sure I understand. Again, this is what I'm doing, okay? What is the problem? Let's make sure I didn't miss anything. Make sure I'm using all the input here. What is this saying here? Graph contractibility. Can a graph isomorphic to H be obtained from G by a sequence of edge contractions, i.e. a sequence where each step replaces two adjacent vertices by a single vertex, adjacent to exactly those that were previously adjacent to at least one of those? Okay? So I think everything I've said so far is true. Okay? So, how would I prove this problem is hard? What's my first step? Okay? What is the first thing I want to do in proving the problem is hard? Okay? Proving it hard, I need to be able to do something. I have a known hard problem, and I want to now, right, sorry about that. I want to now show that by using graph contraction on G and H, that the answer is going to be the same as my known hard problem. So what do I need to do? Okay, I need to pick a hard problem to start from. Which problem smells like the problem that I've got here? Is it satisfiability? Well, satisfiability, again, it's old reliable, but it's not a graph problem, is the way I'm thinking about it. Okay? Is integer partition a good problem to start from? Okay? Subset sum. Well, no. Why is that? It's a number problem. Is this a number problem? No. Okay? Now that starts to smell a little bit like this. Okay? But what were the problems that I said you should start from? You should start from as restrictive a problem as you can. Is subgraph isomorphism the most restrictive problem that we know about like that? No, because we proved subgraph isomorphism by looking at another problem. What was the problem that we based the hardness of subgraph isomorphism on? Clique. Now, clique to me is now starting, again, I don't know how to along here, but clique to me is smelling very, very good. Okay? Why is it? Because in clique, what do you have? You have two problems. Okay? You have two graphs, an input graph and two graphs. And you're asking, is one graph in another graph? That's really what you're asking. Okay? And what's this problem asking? Is this graph in that graph? Okay, by some measure. Okay? Hamiltonian cycle? That might be one to go back to. Okay? That may be a dark horse here. Okay? Because if we think about it, what is a Hamiltonian cycle? Okay? In a Hamiltonian cycle, I mean, I'm not yet ready to abandon Hamiltonian cycle, because we know that if we have a cycle, we just proved that we could squash that down to a vertex. Okay, so maybe that's going to be a useful thing to know about. Okay, so we've now got an idea of which problem we're going to start from, right? I think I'm going to start from clique. Just as this is the way I go about doing it, okay? Actually, in the book, there was a little hint that the guy who proved it the first time started from 3-sat. Okay? But I'm not going to use that hint, okay? Because that's not the way I'd go about doing it. Okay? So what do we want to do with clique? What is the clique problem taking as input? Okay? You've got some graph G and some integer K. What is the first thing that you would think about doing at this point? What would be your candidates, your first candidates to try for G and H? Okay? Okay, I mean, I think that there's an obvious first thing to try to do here. I don't know if it's going to work, but there's an obvious first thing to try to do. Set is G equal to G prime, H equal to the complete graph on K vertices. This is what I would try first of all. Okay? And now I want to ask myself, okay, that if there is a, if I have a graph here, is it true that the only way I can get that complete graph by translation okay, would be if I ended up with that. So is it true, for example, that this graph here, if I can contract it, it had to have had a clique? Is that true or false? How many people are confused about what I'm asking? Okay? What do we want to prove? Here I proposed a reduction, but I have no reason to believe it's right or wrong. Correct? Is it right or wrong?
It's wrong, because if you take the right clique and add an extra vertex on every edge,
Right.
then you suddenly don't have any useful clique.
So what you're saying here is that this is wrong. A graph like this. This graph here, okay, can be contracted to the clique on 3 vertices, but doesn't have a clique on 3 vertices. Correct? So it's not true that just simply giving this reduction, okay, is going to do what I want. Okay? How many people are with me here? Okay? I'm not sure where I'm going next, so I want to make sure people are here now. Okay? So it's clear that right now my first thought didn't work. Okay? Why didn't it work? Certainly if the graph had a clique in it, I was able to squash it down to that clique. Because I could take every other edge and squash it, squash it, squash it into my clique. Okay? But it was not true, so my reduction worked one way. Okay? If I do graph contraction to my clique and it says no, I can't make a clique from it, then that meant that the graph did not have a clique. Okay? But it's not true that if the graph did have a clique, okay, that I would necessarily find it. Okay? I might be able to make a clique the wrong way. Okay? Any questions about that? Okay? Faced with a little bit more of a pickle. Okay? How do we now do the translation? Okay? To sort of force that. See, the way that I want to think about it now is I know what graph contraction is. My strategy is I'm given as input one graph that's a general graph, okay, and one other graph that I'm making it from scratch. The basic idea I think is going to be I want this other graph to be some simple graph, something like a clique. Let's think. Is there any way I can do this? Now, what if I ask for, let's say, empty? Let's say my graph was not connected. Now, what am I trying to think now? I'm now trying to figure out special ways I can transform graphs using this graph contraction. Okay? What other properties of graphs do I know? Is there any way I can disconnect it by doing graph contractions? Doesn't look like I can. Okay, so that seems to be a problem. What happens if I have a big independent set? Let's just think about it in a graph. Is there any way that I can preserve a big independent set in my graph by doing contractions? Okay. What happens if I have a big independent set? Then that would seem to me that I could. What? Well, what happens if I have a big independent set? Certainly I can squash it. I can squash my independent set by using edges that, what do you call it? If I have two vertices that are not connected, I could certainly squash them together using intermediate vertices. Okay?
Then they might not necessarily be independent anymore.
Okay, let's think about it. What other problems might be hard to do? Okay?
You could try to have a binary tree as your instead of the clique.
One idea is now I'm trying to come up with a special restricted graph here. What can I come up with? The suggestion was, could I use a binary tree? Okay, maybe I want to come up with a special graph to translate it to. What about just a path? case. Okay, let's think about that. Suppose I want to get a big cycle in the graph. Okay? How could I squash my graph down to a big cycle? Okay? It would seem to me that this maybe has some hope. Clearly, it's going to be easy to take any graph and squash it down to a single vertex, correct? Because by squashing edges, we make everything denser and denser. Maybe it's hard. What is it about this graph contraction that's going to be hard? Maybe it's not hard making small graphs, because it's easy to sort of squash everything in a compactor. Okay? Maybe it's hard to make big graphs that have very few edges in it. My current thinking. Okay? How hard would it be to come up with, to squash our graph into a cycle here? Okay? One thing that seems to me to be true is if I have a cycle, let's say I have this big cycle. This is my graph, target graph H, is a relatively big cycle. If I want to make this graph, this cycle has a lot of empty space in it, doesn't it? There's a lot of edges that are not in this graph. Okay? So now what am I thinking is maybe I can do something with independent set, squashing it down to be some kind of a cycle, okay, or a path maybe. Okay? Why? Because there's very, very few edges here. If I have a couple of vertices here, there could never have been an edge between here and here, because if there ever was an edge between here and here, it would still be here. Correct? After the contraction? So what happens now if you give me an arbitrary graph, and here is an independent set in that graph of k vertices? Is there any way, can I necessarily find a way to squash everything down such that this thing stays something like a cycle? How many people are seeing what I'm thinking about now? How many people are completely lost? Okay, well, I'm just musing on the fly. But now I'm getting warmer, I think. Okay? What are we trying to do? We're trying to translate some kind of an NP-hard problem. Let's say finding the maximum independent set in a graph G. Does maximum independent set in a graph G, is there an independent set of size k? Okay? Suppose I'd like to solve that using graph contraction on some graph G prime and H. What I'm now thinking is, what if I set H to be something like, and maybe I'm going to go wrong, okay, I don't guarantee it, but what if I set H prime, H to be a cycle on k vertices? Okay? And now ask the question, can I squash this graph down to a cycle, okay, by, what do you call it, by doing that? Question.
Well, the independent set graph could be connected, right? We can require that and it doesn't hurt.
The independent set graph has to be connected, right, because we could always find independent connected.
Okay.
Right, so independent set is hard on connected graphs.
And if
is
we
what
now
you're saying.
make our H a simple path, not a cycle,
Right?
then we can squish the left thing if it was
Okay.
independent to that path.
So what's the question? Okay, Ingmar's saying instead of using a cycle here, what if I create a path on k vertices? Okay? Okay, suppose let's say I have now I have an independent set here on k vertices. Can I squash it so that I get a path as what I'm left with? Okay? It seems to me that if I have any vertex that's adjacent to this, what can I do? Can I squash that vertex into this? Is that going to close off my cycle in any way? So suppose, let's say I do now have something like this, some vertex out here. This vertex is adjacent to a bunch of things, but my independent set remains pristine. If I squash this vertex, contract that edge, what's going to happen? Okay? This vertex will come in contact with that. The neighborhood of this is going to be the same neighborhood we had before. Okay? Except now there's going to be an edge like this and an edge like that. Okay, maybe this isn't going to work so well. Okay?
Well, you want to have that kind of path at the end, right?
Well, but what happens if I now have a vertex here? Let's just think about it. What if now I have a cycle here, my independent set, and I have some vertex here that's adjacent to everything? If I squash this edge, what now happens?
Complete graph, okay.
Okay? Now what I've got is this new vertex is now going to be adjacent to everybody.
Yeah.
Okay? So it does look by doing the squashing. Okay? How many people see does people see where the problem is? Okay? It's not true like I thought it was. Okay? That by squashing, okay, to avert two unrelated vertices, okay, that in fact I would get, that I would preserve my holes, okay. Okay, so how people sort of see that, okay. Any questions or confusion, okay? So still looks like I'm having some problems here, okay. Any other ideas that we might be able to do? Okay, I can't seem to preserve holes. Okay, I can't seem to preserve cliques. Okay, although it smells a little bit right. What other things might I try? I had this idea of using cycles, Hamiltonian cycles. Okay, is it possible if I have a big graph? Just now trying to think about this. Is there any way I can create just a cycle? And it looks like I'm sort of doomed because any vertex that spans the thing is going to get squashed. But what if I squash all vertices that were not in my cycle? Okay? Suppose, let's say I took any edge that goes between anything outside my thing. Is that going to do the trick? Okay? Maybe this is an idea. Okay? Suppose, let's say I've got a graph here. Okay? And I have a pair of vertices outside my chosen clique. Okay? If I were to squash these two vertices, do I add any edges between things in my independent set? No. Okay? Here may be the lever that I need. Okay? What am I saying? I've got two vertices outside suppose, let's say there was this independent set in that graph. Suppose I want to make that thing stay as much like an independent set as possible. What can I do? So long as there are two vertices outside the thing that are connected, I can squash those together, and the only edges that I'm going to be creating or changing are between that new vertex that I'm creating. Correct? So now it's starting to look better. Okay? Because remember, what was my input problem? Let's go back to the problem again. The problem was asking, okay, well, let's zoom in here. Still got 10 minutes to go. Maybe I'm going to come up with something. Okay? Can we find a way to compress this thing? Can we find a sequence of edge contractions? Which means that I'm allowed to specify a series of edge contractions, the order in which they happen. Okay? What if I do something like this? Here I've got a graph. Suppose in my graph G, I've identified that this is going to be an independent set. Correct? Zoom out a little bit. And I now take any edge that is outside, where both the vertices are outside my chosen set. Squashing them will leave me with what? Okay? It's going to leave me with an independent set here. Okay? So certainly if I know in my graph an independent set, I can find a sequence of contractions such that I keep removing any edge that exists outside this thing. Okay? Does anybody agree? Because if now I have an edge like this, what am I going to do? I can now say, let me replace this edge by a different vertex. These two vertices go. Delete those two vertices. Now I've got a graph with one less vertex. Okay? Now what I claim I've got is a situation where if I have an independent set, I can squash it down so that what I've got is an independent set of vertices, okay, and any vertex outside is going to be adjacent to none of the vertices outside my independent set will be adjacent, correct? I could do that if I have this thing. Now I've got something that's almost like an independent set problem. Okay? Why is that? Now what I've said, I'm going to change my problem slightly. Okay? Suppose, let's say that the hard problem that I wanted to prove, the problem I want to prove hard, was can I contract it to a problem where I've got my graph and some other vertices, none of which are adjacent. That's really what I'm sort of doing here.
So basically you create a forest of trees of height 1.
Right.
Does that help to know?
Okay, so wait, so let me just think a little bit more about this. Now what's the problem here? Okay, I need to find some way to get rid of all these vertices. What if I have one vertex out here that I start out being adjacent to everybody? Okay? Suppose I now ask myself, is the graph that I'm trying to realize? Okay? Suppose the target graph I want to realize is a star on k plus 1 vertices. Okay? Maybe this is going to be a hard thing to realize. Okay? In fact, this I think now might actually do it. What's my reduction? Okay, I think I'm getting close. I want to now prove that maximum independent set on G and K is going to be the result of graph contraction, okay, on some graph G prime, H prime. The graph G prime I'm going to construct is G plus one vertex adjacent to all. H prime is going to be equal to a star on k plus 1 vertices. Okay? Let's think about that.
Wait, sir?
Yes?
Oh, there, no, I was going to say you should put paper over.
Okay? So what am I now going to try to say? Your input to the graph, and again, I'm not 100% sure this works, but I think it's very, very close. Here's my input graph G, right? You specify this graph arbitrarily. Okay? Here's G. Okay? Here I'm now going to add, as my reduction to create G prime, I'm going to create another vertex that's adjacent to everybody. Okay? And now what I'm going to do is ask, can you create a graph which consists of one center point and k other vertices? Okay? This is what my reduction is. Okay? My claim is if I had a big independent set here, this being an independent set, right? I could certainly squash every other pair of edges down, okay, such that any edge between any other vertex can get swallowed up by this new global vertex that I added. Okay? So what am I saying here? I think this is actually, this might actually be right. We have to think about this. Okay? But I think you should be able to see the intuition of what's happening here. Okay? I now have to specify, my claim is, if I've identified an independent set in this graph, can I then squash it down to create this? And the answer is yes. Question?
Yes, but you need to identify the independent set before.
Oh, but that's the hard problem. I'm trying to say that if, what I'm now going to prove is as follows. Okay? If, what's the problem? Finding a maximum independent set, I'm going to give you a procedure to find maximum independent set if you can do graph contraction. Okay, I've just done it. Okay? What is the point here? If you can do graph contraction, that would mean that you could take this graph and squash it into a star, right? If you could squash it into a star, that meant that there were a bunch of vertices here that never had any edges between them, correct? That was what we showed, that somehow by squashing them you could create edges, but if there was never any edge, you could never delete any edge between two vertices, except by squashing the two of them together. So what's the argument? If you take the original graph, add that extra vertex to it, okay? If there is a way to, what I'm claiming now is if there is a way to contract this to that, okay, contract this new graph to the star, that meant that all of these vertices could never have been involved in a contraction. Okay? Why? Because this big bad vertex, okay, is always going to be adjacent to everybody, no matter how you squash it. So the descendants of the big bad vertex are going to become this guy. The independent set here is going to become these branches of the star. Okay? And my claim is now I've given you an algorithm. Okay? Here, if this graph has an independent set of size k, then I would have come up with a way to squash this to this. If so, let me identify what these vertices were. Those vertices have never been squashed. They're virgin vertices. And they have a unique identifier back in the original graph. So in the course of squashing this to this, I had to have preserved these vertices. Okay? So if you have, give me a graph contraction of this and this. This thing will have a graph contraction, okay, if and only if this thing has an independent set. Okay? Graph contraction is the same as maximum independent set. Maximum independent set is the same as graph contraction. Neat, sweet, NP-complete. Okay? I have to go through, and there's probably some details that have to be verified, but I'm pretty sure I'm right about this. Okay? And I think this actually should be convincing. Okay? Because really what I'm saying is now, if there's a graph contraction, I've just proven, that gives me this, there had to be this underlying independent. Okay? And now if there was an independent set, there's a way to contract it. Well, sure, if there is this independent set, I can squash everybody else, okay, that's not in the independent set to this big vertex. And then what I'm going to be left with is this. Okay? This problem is the same as that, neat, sweet, NP-complete. Okay? This was not an easy reduction. Okay? But I did it on time because now there we go. Okay? Any questions about how you do it? Okay? This was not an easy one. Okay? But again, if you attack it logically, what was it that made this thing hard? This thing was hard because you had an independent set. Okay? And that was what we had to smell. Okay? Once we smelled it, we kept beating on it, eventually we got it. Question? Would a problem like this be on the par with the final? This is a harder reduction than I ask on the final. Don't worry about that, okay? But on the other hand, I hope this was useful, okay? This is not that hard, okay? I was brave enough to do it because I know these reductions can be banged out if you think about it. Thanks a lot. Take care. Talk to you next time.